Okay, we're going to start off this video looking at example 13.7 from the textbook. This involves thermal expansion. It specifically looks at volume or three-dimensional expansion due to temperature changes. So in this example we have a gas tank that is 70 liters. That's its volume, and it is filled all the way to the top with gasoline on a 20 degrees Celsius day. Now we're going to say that that car sits in the hot sun and the temperature increases to 40 degrees Celsius. What is going to happen here? So both the tank itself, which is made of steel in this example problem, and the gasoline are both going to expand. So we need to take a look at their relative expansions to see what's going to happen. So if we look at table 13.1, we can see here the coefficient of expansion for gasoline, is 950 times 10 to the negative sixth. So we can take a look at how much it expands. So for three-dimensional expansion, the change in volume, delta V, is equal to beta times V naught times delta T. Okay, the delta T in our problem, we started off at 20 degrees Celsius, and the final temperature was, let's go back and look, was 40 degrees. So our delta T is going to be equal to 40 minus 20, which is 20 degrees Celsius is our change in temperature, delta T. So the change in volume is equal to 950 times 10 to the negative 6, that's the beta value from over here. And we're going to multiply that by the initial volume of our tank, which, if we take a look back here, was 70 liters. Times our delta T, 20 degrees Celsius. Now, normally we would want to use meters to the third power for units of volume. So liters are not a typical unit of volume that we would use. But in this particular case, it doesn't really matter because the units of beta are Celsius to the negative 1 power. And when we multiply that by degrees Celsius, it's just going to cancel out. And so our change in volume is just going to be whatever units we use here. So if we had used cubic meters, the delta V would be in cubic meters. Or since we're using liters, our delta V turns out to be 1.3 liters. So the gasoline in the tank is actually going to expand. It's going to increase in its volume by 1.3 liters. Now let's take a look at how the tank itself is going to expand. If we look at solid material, steel has a coefficient of thermal expansion of 35 times 10 to the negative sixth. Right off the bat, that should indicate to us that we are going to have a potential problem here because that is less than the gasoline by a significant margin. That's for gasoline, it was 950 times 10 to the negative sixth versus only 35 times 10 to the negative sixth. So let's see what happens here. So for the steel tank, the delta V is going to equal beta V naught delta T. And so that's going to be 35 times 10 to the negative sixth times our initial velocity was, or not velocity, volume. The initial volume was 7 liters. And our delta T is 20 degrees Celsius. So if we multiply that all out, we get a change in volume, delta V, of only 0.049 liters. So if the gasoline expands by 1.3 liters, and the tank is only getting larger by 0.049 liters, the difference between those two is going to be about 1.251. But if we round that to two significant figures, that's just going to round right back up to 1.3. So approximately 1.3 liters of gasoline are going to spill out of this tank. So why doesn't that happen? Why doesn't that happen on your vehicles on a hot day? Well, first of all, gasoline tanks are made with this type of expansion in mind. They allow for expansion to occur. So you would never really fill a tank up to the very top where it's brimming over. So it doesn't actually happen, but the change in volume expansion does. So one interesting kind of exception to the rule that things expand when they are heated up and contract when they get colder is water. And the reason for that is because water reaches its smallest volume. Whoops. Get rid of that. At 4 degrees Celsius, approximately 4 degrees Celsius. So that is slightly above freezing. And then once it begins to freeze, the volume of the water actually begins to expand. And that has to do with the way the molecules are arranged. So we don't need to get into that in terms of why it happens, but we do need to be aware that it does happen. And you may already be familiar with this, actually, because if you've ever left a can of pop in the freezer, you've and forgotten about it, you may have observed that the liquid inside expands, and in fact will sometimes cause it to explode and burst the can. So I found this meme. It's pretty exciting if you leave it in the freezer and it doesn't explode. So what if we have an object that wants to expand and contract due to changes in temperature? Let's say we've got a rod of some type, and we change the temperature. It wants to expand and contract, but we don't allow it to. We fix its ends in some way so that it can't move. What happens in this case is that an internal stress occurs. So it's related, how much stress occurs is related to the change in temperature as well as the modulus of elasticity of the material, E. And so the stress, force divided by area, equals alpha, the coefficient of expansion, times the modulus of elasticity, times delta T. So we can calculate the amount of stress induced in a material by thermal changes using this formula. So we've spent some time now talking about how we can change the volume or length of a material by changing its temperature. So for a moment here, let's move on from temperature and look at pressure. And so pressure and volume are inversely related. And this works best when we talk about gas, because gases can be compressed by applying pressure. Solids and liquids, it's very difficult to change their density, but with gases we can. And so this relationship between pressure and volume is an inverse one. So at relatively low volume, we have high pressure. So, or maybe it's best to think of it the other way around. When we apply a high amount of pressure to a gas, we can decrease its volume. And when we lower the pressure on a gas, its volume will increase. And this is basically the essence of Boyle's law. This is Boyle. And Boyle is the one that stated that pressure and volume have an inverse relationship. So I always like to think of this as squeezing a balloon, right? So if we were to squeeze a balloon and increase the pressure on it, we could shrink it by squeezing it. And if we apply less pressure to it, it will expand. I've got a little PowerPoint animation here. So in the first case, we're adding more pressure, and that's going to cause the volume to decrease. Over here, if we decrease the pressure, the volume will increase. Let's move on to the next section here, 13.5. So if we measure the volume of a substance at varying temperatures, like we have done with like the gasoline and the gas tank problem, as the temperature decreases, as we go left along the x-axis here, the volume goes down. The volume along the y-axis goes down. And it goes down, down, down in a linear way. Well, what if we extrapolate that line, take it all the way out to see when it hits a volume of 0? Is that possible even? Can we get the temperature so low that the volume becomes 0? And it turns out, in theory at least, we can. And that temperature is called absolute 0. So if we trace this line all the way back, we'll see that it hits the x-axis at negative 273.15 degrees Celsius. This temperature is known as absolute 0. This is the temperature at which volume would become 0. And essentially what it is it's the temperature at which the individual molecules, the atoms that have energy and are moving around, they're kind of moving around and vibrating at absolute 0. This is the point at which all of that motion would stop, that they just cease to move around. Lord Kelvin is the scientist most associated with absolute 0, and that's why we call the Kelvin scale, it's named after him. So it's similar to the Celsius scale, except that instead of 0 starting at the freezing point of water, in the Kelvin scale, 0 is absolute 0. So it starts at the coldest theoretical possible temperature. And then we start going up from there. And 1 Kelvin is equal to 1 degree Celsius. So their units are the same. It's basically the starting point is different. So in the Kelvin scale, the freezing point of water is 273.15 Kelvin, because we started all the way back at absolute 0 and worked our way up. And then the boiling point is 100 degrees greater than that, 373.15 Kelvin.